Potentiometer, calibration of a low range voltmeter with the help of a potentiometer. So our aim of the experiment is to calibrate the given low range voltmeter with the help of a potentiometer. Coming to the theory of calibration of a low range voltmeter using potentiometer, as we know, if L is the balance length of the potentiometer, which balances a Daniell cell of EM of 1.08 volt, which is connected in the secondary circuit, then we are getting the potential difference per unit length of the potentiometer wire is 1.08 divided by L, that much volts. So instead of a Daniell cell, if you are connecting a voltmeter in the secondary circuit, and if L1 is the balance length which balances a voltage V0, where V0 is the voltmeter reading, then the calculated voltmeter reading or the calculated reading or the potential difference across the voltmeter V should be 1.08 by L into L1 volts. Here V0 is the voltmeter reading that we can observe, and V is the calculated voltage across the voltmeter, which is 1.08 divided by L into L1, where L1 is the balancing length at present. Now coming to the procedure part, now we have the potentiometer. Between A and B, we are connecting the primary circuit with accumulator and rheostat, and in the secondary circuit we are connected the Daniell cell, or we are connecting the Daniell cell through a galvanometer, and let L be the balancing length corresponds to the Daniell cell that is initially determined. Now we remove the Daniell cell from the secondary circuit, and we are connecting a voltmeter in the secondary circuit. Then the voltmeter reads a voltage V0. We can mark that reading V0 in the tabular column. Then find the corresponding balancing length L. Then we can calculate the voltage across the voltmeter using the formula 1.08 by L into L1 volts. Then we are determining the value of V minus V0, where V minus V0 is calculated, that gives the correction in the value of voltmeter reading. Now we can repeat the experiment by taking different positions. That means V0 value is changing, and for each value of V0 we are taking the L1 value, and then the corresponding V value is calculated. So the experiment can be repeated many times, and we are plotting a graph between the V0 value along the x-axis and the correction value, that is V minus V0, along the y-axis. Then we are getting a irregular or zigzag graph, and that is the calibration graph. Coming to the observations, we first note the EM of the Daniell cell is 1.08. The balancing length of Daniell cell is noted, that is L, we obtained. Then PD across the potentiometer wire is calculated using the formula 1.08 by L. Then we connect the voltmeter and let L1 be the balancing length for a voltage reading, or when the voltmeter reads 0.1, but voltmeter reading 0.1, we obtain a balancing length L1. Then we calculate the voltage V 1.08 divided by L into L1, that is nearly 0.1, and then we will calculate the difference between V and V0, that is the correction is calculated. Now the experiment is repeated, keeping the jockey another position, so that the voltmeter reads 0.2, the balance length is obtained, the voltage is calculated. So we obtain the calculated value of voltage is obtained, that is nearly somewhat near to 0.2 volt. Then the experiment is repeated for 0.3, 0.4, 0.5, 0.6, etc. voltages, and each time we note the voltmeter reading and the balancing length, and from the balancing length the calculated value of voltage is determined, and then a graph is plotted between V0 along the x-axis and V minus V0 along the y-axis, that is a calibration graph. So the given voltmeter is calibrated. Now let us see the experimental setup for the calibration of low range voltmeter. We are provided with a potentiometer here. As we all know, the potentiometer consists of a uniform wire which is arranged in 10 rows. So it is having a total length of 10 meter. 10 rows are there. It is connected between two terminals A and the terminal B. Now between A and B we are having the primary circuit. Now for the primary circuit, we are having an accumulator here. Now the positive of the accumulator is connected to A, and from the negative it is connected to a key here. A key is connected here. Then from the key a rheostat is connected. From the rheostat it is connected to B. So by moving the rheostat, we can vary the current that is passing through the potentiometer. So that is the primary circuit. Now in the secondary circuit, initially we want to include the Daniell cell. We want to find the balance length for a Daniell cell. Here we are having a voltage source, and this source provides the Daniell cell voltage, that is 1.08. So there is an arrangement is here. So that Daniell cell is connected here. Now it is connected through a galvanometer. We are having a galvanometer here, and this galvanometer is connected to a jockey, and that jockey can move over the potentiometer wire. Now after giving connections, if we are giving contact at the end A, we can see there is a left deflection, and when we are giving contact on the other side, we are having a deflection on the right side. So the connections are correct. Now we want to balance it. We can move the rheostat, so we can get the balance length for the Daniell cell, or we want to we can fix the balance length for the Daniell cell. I like to fix the reading at 720, that is on the 7th row, corresponds to 20 on the scale. So at 720 I want to balance. So we are giving contact at the point 720, and then the rheostat is adjusting in order to get a balance length of 720. If you want to change 720 to another value, that is also possible. Now when the jockey is giving contact at the first row, we are getting a left deflection, and on the last row we are getting a right deflection. So we are supposed, or we are planning to get a balance length at 720. So if jockey is kept pressed at 720, then the rheostat is adjusted. So as to get a zero deflection. Now for a particular position of rheostat, we are getting a zero deflection. So the balance length corresponds to the Daniell cell is, now it is 720. So we are getting zero deflection. Now for the second part, the Daniell cell is removed, and instead of the Daniell cell in the secondary, we are connecting the voltmeter alone, no need of galvanometer. The voltmeter is alone is connected in the secondary circuit, and the voltmeter is connected to the jockey, and give the contact at some point such that the voltmeter reads 0.1. We want to find the balance length corresponds to 0.1 volt. So we are moving here. Now it is having a particular value. Now corresponds to 0.1. We have to find out the value. Now here, when it is given contact at this particular point, now this point is at 70. Now at this particular point 70, the voltmeter reading is 0.1 volt. We can see 0.1 volt here, and the balance length is 70 centimeter. Now again we are repeating. We are supposed to get a voltmeter reading of say 0.2 we want. So we are moving again on the potentiometer wire. Then we want to read 0.2 volt. Now it is almost 0.2 is here, and we obtain the balance length here. Now here the balance length is 140. Now for 140 it is balancing at 0.2. So 0.2 volt is balanced by 140. So the balance length L1 is 140. Again it is repeated so as to get a reading of 0.3 we want. Now we want to move again the wire. Now it is 0.3. Now it is at a distance of 220 or 220. We are getting a balance length for 0.3. Similarly, it is moved to get a balance length for 0.4, 0.5 and 0.6, 0.8 and 0.9 volts. Each time we are determining the balance length, and we are calculating the value of V, calculate the value of V, and then V minus V0 is calculated. Coming to a sample set of reading in the calibration of the low range voltmeter, the EM of the Daniell cell is 1.08. We obtain the balance length for the Daniell cell as 720 centimeter. So PD across the potentiometer wire is calculated 1.08 divided by 720, that is calculated. Then in the secondary circuit, when we connect the voltmeter, when the voltmeter reaches 0.1, the balance length is 70. That means when the jockey is contacted at 70, the voltmeter reaches 0.1. Then we calculate the value of voltage, that is 1.08 divided by 720 into 70, that we obtain 0.105. Then V minus V0 is calculated, that is equal to 0.005 volt. That is a correction in the first case. Then the experiment is repeated for 0.2. We obtain the balanced length 145 and V is calculated, that is 0.2175, and the correction is calculated. Similarly, it is calculated for 0.3, 0.4, 0.5 and 0.6, 0.8, 0.9 and 1 volt. Each time we obtain the balanced length and the value of V is calculated and V minus V0 is tabulated. And using that value V minus V0 and this V0, a calibration graph is plotted, and so we obtain the result. The voltmeter is calibrated and the calibration graph is plotted.